Gravitational potential energy, a fundamental concept in classical physics that quantifies the energy an object possesses due to its position in a gravitational field. Gravitational potential energy is given by the equation U is equal to mass, m, times acceleration due to gravity, g, times height from the surface, h. It shows how much gravitational potential energy an object at height, h, has due to gravitational field with respect to the surface. But is that all about gravitational potential energy? No, it's not all. Let's first understand what gravitational potential energy really is. An object at a certain height falls on the ground due to gravity. For the object to fall, it must do work. The work done shows the amount of energy required for the object to fall on the ground. As we know, work done is equal to force times displacement. In this case, force is the weight of the object and displacement is its height from the ground. And this is the derivation for the formula of gravitational potential energy. Here, the ground is taken as the reference point for the calculation. So, any object above the ground will have positive potential energy and zero on the ground. But what if the object is below the ground? Will it have negative energy? What does it even mean for the object to have negative energy? Gravitational potential energy of an object depends on the choice of reference point. But that is not what we really care about. What we really care about is the change of gravitational potential energy. The change in energy is same when the body falls from height, h1, to height, h2, regardless of the reference point. It does not matter if the gravitational potential energy of an object is positive, negative or zero and where the reference point is. We care about the change in the gravitational potential energy. But there is another problem. The value of g is not uniform at all height, it changes. And what if we chose the reference point at infinity? It turns out that the equation, U is equal to mgh, is only accurate for calculation near the surface. Where the value of g is almost same and the reference points can be at finite distance. For cosmological scale, there is more general formula for gravitational potential energy. Let us consider a massive body with mass, capital M, and radius, capital R, and an object with mass, small m. The gravitational force at infinity will be zero. So, at infinity the gravitational potential energy will also be zero and will be the reference point. When the object gets closer and closer to the massive body, its gravitational potential energy decreases. Since the gravitational potential energy is always zero at infinity and decreases while getting closer to the massive body, the gravitational potential energy is always negative. As we know, gravitational potential energy is the work done for the object to fall. But in this case, gravitational potential energy is the work done to get the object at distance, small r, from infinity. We know that W is equal to force times displacement. Force is the gravitational force between the massive body and the object, but it is not constant. So, we have to integrate the gravitational force with respect to distance between them, small r. So, work done is equal to integral of F with respect to small r from infinity to r. After some simplification, the formula for the work done comes out to be minus g, capital M, small m, divided by small r. Since gravitation potential energy is the work done by the object, the formula for gravitation potential energy is also U is equal to minus g, capital M, small m, divided by small r. This equation also shows that the gravitational potential energy is always negative and is zero at infinity. To sum up, we learned that the gravitational potential energy is the work done by the object to change its position in the gravitational field, and we mostly care about the change in the gravitational potential energy. We also derived the two formulas of gravitational potential energy, U is equal to mgh for small scale and U is equal to minus g, capital M, small m, divided by small r for cosmological scale. We also learned that the gravitational potential energy is always negative and increases as we go far and is zero at infinity. With gravitational potential energy, we can determine the escape velocity of a massive body. But that's the topic for another video. Till then, thanks for watching.